Section 5.6 is inverse trig functions. We're going to take a look specifically at derivatives in this section, and then in 5.7 we'll look at the antiderivatives or the integrals. One thing I want to make a comment about at first is as we're taking a look at, well, it's further in this packet, but as we're taking a look at the derivatives of the inverse functions, these are ones that are not appearing today on your gateway, obviously, because we're just learning them today. So it'll be on it's the second page of your notes. But when you do get to your exam, right, that's next week, I will expect that you've memorized them by that point, okay? They just don't come up quite as frequently, generally speaking, and so it's not something that I want to continually, repeatedly, testing you over all the time kind of thing, which is sometimes what happens with the gateway with things. I'm not interested in it being that huge of a deal. The other ones that we've done up to this point are much more prevalent, and so they're much more important that you memorize them in detail and be able to use them more frequently. All right, so to start with, we're just going to remind ourselves some things about trig. And it's probably been at least a year since everyone's taken trig, at least, right? Or more. So these are some that you may or may not sort of remember. I'll talk about where they come from as we're going. But we're going to do 3 of them at a time because that's all that fit on my screen. All right, so our first inverse trig function is arc sine. You've probably heard them referred to as the inverse sine. Throughout Calc 2, we will call them arc trig functions, and we will use the ARC notation as a prefix. We don't want to think that that -1 somehow infers an exponential power, which it sort of looks like. And since we do a lot with exponents in calculus, we just don't want to confuse the notation. The domain for arc sine is -1 to 1, and the reason that's the case is because the range for sine is -1 to 1. Think about the graph of sine itself. It bounces up and down between 1 and -1. So the domain for arc sine is from -1 to 1. You'll notice some interesting things happening with the range. The range on arc sine is -pi/2 to pi/2. The reason that's the case is because if you use any bigger of an x value window on sine, you won't have a 1-to-1 function. We've talked about 1-to-1 functions in this class, right? If they pass the horizontal line test, they're 1-to-1, and if they're 1-to-1, they can have an inverse. Well, in order to do the inverse, they have to be 1-to-1. Well, sine, that is sine y equals x, the graph of sine is only 1-to-1 if the domain is between -pi/2 and pi/2. That's the restricted window. So that means correspondingly that when we do the arc sine, the range and domain switch, so now the range is going to end up being -pi/2 to pi/2. And if you're thinking about unit circle kind of values, this actually ends up giving unit circle values in quadrants 1 and 4. Okay, so the right-hand side of your unit circle. And again, the reason is because if you were looking at the sine values, say at the top 2, right, in quadrants 1 and 2, what you end up getting is you get the sine values in the quadrant 2 are exactly the same as the sine values in quadrant 1. They repeat themselves because sine is the y value of your unit circle, right? So that's why you're restricting it to quadrants 1 and 4 instead. And of course, 1 and 4 also correspond to this -pi/2 to pi/2 business. All right, arc cosine, you see the same domain, of course, for the exact same reason. The range is 0 to pi. So sine and cosine, of course, are really the same graph. They're just shifted from each other. So it makes sense that the range would shift as well. So again, if you think about the graph of actually cosine, the graph of cosine, if you go from 0 to pi on y equals cosine x, that graph would be 1-to-1. So then when we switch the domain and range, because we're doing the arc cosine, we also switch it to being from 0 to pi for the range. And again, just like quadrants 1 and 4 work for sine, quadrants 1 and 2 work for cosine. The cosine is the x value. So the x value along the top of the unit circle is a unique value at no matter which value you point on the unit circle you're at. Arc tangent. Now tangent's different, right? Because tangent's got asymptotes, and tangent has this sort of repeating values that are -∞ to infinity on the range. Well, that's true, right? -∞ to infinity for the range of tangent. So when we switch domain and range, that becomes -∞ to infinity on the domain for arc tangent. The tangent values are trapped between -pi/2 and pi/2. Like if you look at one of the periods of tangent, that would be one period of it. So that's the domain in tangent, so that's the range in arc tangent. It's the same 1 and 4 that we got on arc sine. And then the other thing you'll notice that's different between arc sine and arc tangent is, of course, the range has the parentheses instead of the brackets. Because what happens at pi/2 and -pi/2 for tangent? Asymptotes, right? we can't actually have those values. So that's why we've got the parentheses there instead of the brackets there. But we don't have those asymptotes for arc sine, so it's perfectly acceptable to have the endpoints. All right, we've got cotangent, secant, and cosecant. And I could find no better solution for the way that I've written these. You have more space when you're writing from left to right on your paper, so feel free to not have this weird thing going on where I've got the U on the second line. I couldn't fit it across my screen without making it so small you couldn't have been able to read it. So the first one, cotangent, that one's simple enough. It looks a lot like the screen before. The arc cotangent of x has a domain from negative infinity to infinity, just like tangent did. The range is from 0 to pi for exactly the same reason that the range was negative pi over 2 to pi over 2 for tangent, and it's quadrants 1 and 2 as opposed to 1 and 4. All that's the same. Secant and cosecant are a little different. And the reason they are is because if you'll remember those graphs, the period, from one place to the next where it actually starts repeating itself, has an asymptote smack dab in the middle of it. So you have these sort of U-shaped curves that go down and then up for cosecant and for cotangent. Does everybody remember that? They're kind of like these, U's in the sky and U's down below the earth or something like that. We've got these U's everywhere, and right and smack dab between them, every time there's an asymptote. So you notice, for instance, on the domain, on the range is what I meant to say, that the range is from 0 to pi, but the y cannot equal to pi over 2. So similarly, you could write it 0 to pi over 2 to pi. So you could write it more like we wrote the domain if you wanted to. That would be okay. The domain is from negative infinity to -1 and 1 to infinity. And again, if you'll remember, the reason or the way that that works is because those u's actually avoid everywhere where sine and cosine graphs are. Sine and cosine goes between -1 and 1. So when you take the reciprocal, which is what cosecant and secant are, the reciprocals of sine and cosine, you don't get the middle part of the graph between -1 and 1. So you have this sort of awkward jumping up, sort of ness of the graph. So your domain actually goes from negative infinity to -1, and then from 1 to infinity. The quadrants match the same as they were. So the secant quadrants are 1 and 2, just like they were for cosine. The cosecant quadrants are 1 and 4, just like they were for sine. Okay? So the first thing that we're going to do, and I hope that you've got some of these unit circle kinds of values in your mind. If you don't, now would probably be a good time. That is not immediately right now, but at some point, this evening or whatever, when you start working on these, to print out a unit circle from the internet or something like that so you can reference it until they're sort of back in your mind again. What we're going to do is we're going to evaluate some of these things by hand. So in very much the same way that all the sections up till now have started out, we've looked at the algebra component of whatever's going on first, and then we've moved into the calculus. We're looking at the trig component, the pre-calculus, trig component of what's going on, and then we'll look at the calculus component. Okay, so the same pattern of what we're doing. All right, so for some people, this is how I always do it when I do trig, is that I set this equal to some variable, and it doesn't really matter what letter. It looks like I've got x in my notes, so I'll use x on here as well. It helps to see this rewritten without it being in an arc trig function notation. For example, since this is the arc sine of 1/2 equals x, it's the same thing as saying that 1/2 is equal to the sine of x. And in some sense, it's not exactly accurate, but it's a fairly accurate representation. What you're doing is you're doing the sine with that angle as with that value as the angle. Let me say it that way. And then, of course, sine and arc sine are inverse operations as long as you're on the correct interval. And we are, because we're between -1 and 1. Right? And that's what pi over 2, or 1/2 is, between -1 and 1. So they are inverse functions. And so the question here is asking you, where does the sine of x equal 1/2? So the sine graph, since we're all a little bit rusty, I'm going to guess, on our unit circle, the sine graph, as we learned in the last 2 slides or reviewed, is in 1 and 4, right? And if the sine is positive, which quadrant are we in? We're in quadrant 1, so we're up here now. Okay, and if it's 1/2, it's either the 30-degree angle or the 60-degree angle, right, which is pi over 6 or pi over 3. Which one is it? Do you remember?
30.
It's the 30, yeah. It's easy, right? Well, you're looking at me like it is anyway. This is the 30-degree angle, but what is the 30-degree angle in radians? Pi over 6, very good. So this is what we've got as we're looking at this particular one. So we're down here somewhere when we're looking at that. All right, everybody good? Okay. This one is arc secant. So we can do the same thing. Again, there's no special letter. I'll use A here just so that I can show you it doesn't matter what the letter is. I have negative square root of 2 equals the secant of A. I don't really work in secants in my brain very well because I didn't learn the unit circle in secants. I learned it in sines and cosines. So for me, when I see secant, I automatically reciprocal. I do a reciprocal and talk about cosine. So the reciprocal of this would be on both sides. It would be negative 1 over square root of 2 on the left, and it would the reciprocal of secant is cosine on the right. Okay, it's not that I have to do that. It just is easier to think about that way for me. And then what's on the left doesn't really look like any of the cosine values, but if you rationalize, you will see that it is, right? Negative square root of 2 over 2 for the cosine value. Yeah, it is a 45-degree angle. Do you know which quadrant it's in, Abby? Yeah, it's in quadrant 2. How do you know? Right. So for cosine, we're either in quadrants 1 or 2. And it is negative, so it's in quadrant 2. So it's this angle right here. And it is, sort of the reference angle is the 45-degree angle. But in quadrant 2, what is that angle? Somebody said it. 135, which in radians is 3 pi over 2, right? I'm sorry, 3 pi over 4 is what I meant to say, not 2. 3 pi over 4. Talking too fast. 3 pi over 4. It's the 135-degree angle. This step or this one? This one? I did the reciprocal. So the reciprocal of the square root of 2 would be 1 over the square root of 2, and the reciprocal of secant is cosine. They just are reciprocal functions to each other. Okay, any other questions on that one? Because it's about to get more interesting. Oh, did I hear some groaning? What was that about? Okay, so this one has the sine of the arc tangent. So, if this said sine of arc sine, no problem. There are inverse operations, but that's not what this says, right? I have different trig functions that I'm dealing with. So what I'd like to do is isolate this piece right now first. And let's just give that an angle name, and I'll call it theta this time, because Greek letters are fun too. So this means that if I'm working on the inside, I'm asking myself the question, what is the tangent of theta? When is the tangent of theta equal to 3 over 4? Now, this is not a unit circle value, and that's okay. But it doesn't also mean that I necessarily need my calculator for it. The cool thing that I can do once I'm working with angle values that I don't know is I can actually create triangles to work with them. And triangles are easier to work with in many cases because I can use any values instead of looking for specific unit circle configurations that I'm sort of accustomed to seeing. So because this tangent value is positive, I do know which quadrant I'm in. Which quadrant am I in? I'm going to be in 1. So I'm going to draw my triangle up here in quadrant 1. If it had been negative, because it's tangent, what quadrant would I be in? Which one? 4. Okay, so make sure you're drawing your quadrants or drawing your triangle in the right quadrant, because the other trig function that you're dealing with will have. You have to make sure that your angle or that your sine is correct, and if you're in the wrong quadrant, you might very well get the wrong sine. Okay, so here's my triangle. Here's theta right here in the middle. That's the angle theta that I'm referencing over here, right? Tangent in terms of triangles. You guys remember SOHCAHTOA? Right, it's the opposite over the adjacent. 3 is on the right and 4 is on the bottom. How do I find the third side? Right. It is a Pythagorean theorem, but this is probably a Pythagorean triple that you're aware of. It's 3, 4, 5. If you're not aware of it, or if it becomes one that we haven't dealt with, then you would use a Pythagorean theorem to find it. Okay, so everybody good so far? The same reason we were switching them over here. And the real reason I want to, though, Evan, is because I want to create this triangle, so that then I can find the sine value in this triangle itself. I'm not going to find this angle theta in this problem at all, because that's not what I'm asked to do. I'm asked to find the sine of it. So I created the triangle with the express purpose of never having to actually find theta. I have this triangle now that has all the ratios in the right places, all the side lengths and so forth. And I need to know in this triangle what is the sine of theta. 3/5. And how did you get that, Abby? Right. The sine value is the opposite over the hypotenuse. If you go through and you actually find theta, probably somewhere in your calculator you're going to end up with a rounding error that's not going to give you 3/5, which is 0.6. It'll probably tell you somewhere along the way that the angle value is like 0.5976238, I don't know, something like that. Because it's going to round things as it goes, because it does it with numerical approximation, not with a geometric interpretation, like we just did it. And it would be wrong and we would be right, just to clarify that. The calculator is not always right. Numerical approximations don't always give us exact values we want. Okay? I think I have another one of these. I do. A couple more, actually.
Now, if that was all we learned today, that could be good.
The problem is that this is all stuff that should be reviewed at this point. But reviewed potentially from a very long time ago, and I do recognize that. So, okay, so we're going to do this the same way. We're going to start out by calling this angle in the middle some angle measurement. So just for fun, we'll call it beta this time. We're going to use some Greek a little bit today. So we're going to change this then to represent this portion of it as the sine of beta equals -5/6. And the first thing we need to do is make sure we're in the right quadrant. This quadrant will be 4 because the sine values in 1 and 4. So now we're here down here in quadrant 4. You'll remember your triangles always draw the vertical piece back to the x-axis. So right here is always the right angle in your triangle, back to the horizontal axis, the x-axis. All right, so this is the sine value is -5/6. So where does the -5 and the 6 go?
5 is going to be your y-axis, and your 6 is going to be your hypotenuse.
Okay, and I'm going to write it over here on the right-hand side. So the vertical piece is the -5, and then the horizontal, or the hypotenuse, excuse me, is the 6. Now I recognize in a triangle that's not really -5 length. The negative is indicating our direction, right? And it really doesn't matter because when I use the Pythagorean theorem, I'm going to square it anyway, and I'm not going to have a negative. So it's not really truly that important. But I don't want you to think that I'm writing it down somehow incorrectly. It does have meaning. It just doesn't mean that it's a negative length. So at this point, I do need to find the third side of the triangle, right? How do I do that? Yeah, I'm going to have some square roots involved. So I don't know what letter. I used beta, so how about I just call this x, because it's the x value anyway. That'll work. So this is x squared plus -5 squared equals 6 squared. So I have x plus 25 equals 36. What is x? X squared, sorry. What is x squared? 11. So x is square root of 11. And at this point, you need to be careful. I mean, it is either the positive or the negative square root of 11. Why is this one positive square root of 11? Because my x values are on the positive side of the x-axis. Yes, very good. So that's why it matters that we get things in the right quadrant when we do this. Because if I had drawn this up in quadrant 2, I probably wouldn't be putting it in there correctly, right? So be careful. So this is square root 11 down here now, across the top of our triangle, so to speak. And if I'm taking a look now, I'm finding the tangent of beta. Oh, I didn't mark beta in my triangle. I should do that. Here's beta. It's always the central angle at the origin. All right, so the tangent value is what in terms of my triangle? Yeah, opposite, which is -5, over adjacent, which is the square root of 11. And we don't leave radicals in denominators when there are a radical constant, right? If it were a variable, it would be different, but square root of 11 is a constant. So we would rationalize. And then our solution would be -5 square root of 11 over 11. Okay, is everyone good with that? Okay, we're going to make it just a little bit less specific because on this one, I don't have an angle measure, or I don't have a value inside of the arc function. It's a number, it's a variable. Because we don't have it as a variable as a constant, we have it as a variable. By default, we just draw it in quadrant 1. Okay, we don't have a reason to think where it is otherwise, so we just draw it by default in quadrant 1. So in some sense, that's an easier thing to work with than the last ones because I don't have to decide what quadrant I'm in. I'm going to be in quadrant 1. This right here, we'll give it the name gamma. So this is the secant of gamma is equal to x. Okay, so gamma is right here. How do I do secant? Well, it's the reciprocal of cosine, right? What would cosine be? Adjacent over hypotenuse. So what will secant be? Hypotenuse over adjacent. Now, this doesn't look like there's anything there for it to be, so it's x over 1. So this should be the hypotenuse, which is x, that's right here, over the adjacent, which is right here, 1. Hypotenuse over adjacent instead of adjacent over hypotenuse, because that's how cosine and secant are related. Finding the third side, that's a Pythagorean identity issue, right? So we need to figure out what this side is. I'll call it y for the moment. I know from Pythagorean identity that 1 squared plus y squared equals x squared. And you might be looking at this and saying, but there's 2 letters. There's x and a y. How do I know which one to solve for? Well, remember, our whole goal is to figure out what this value that I just created arbitrarily, y, is in terms of x. So it's y that I'm solving for. So as I'm working through this, I'm going to get y squared equals x squared minus 1, because that's what 1 squared is. So y is the square root of x squared minus 1. So that's what's going on right here. Square root of x squared minus 1. So then back in the original problem, we want the sine of that gamma. Sine is what over what?
It's going to be the square root of
Okay.
x squared minus 1 over x.
It's opposite, which is square root of x squared minus 1, over hypotenuse, which is x. Okay, is everybody okay with that? Because the next thing you're going to do is you're going to write down a whole bunch of derivatives. I know. A whole bunch of them. All right, here's our first 3. The derivatives of our arc trig functions. Arc sine is 1 over the square root of 1 minus x squared. Arc cosine, how closely is it related to arc sine? Wow, it's like the same thing with a negative, isn't it? Yeah. And then arc tangent looks like we've squared, kind of like we've squared the numerator and the denominator separately, and you've changed the sign in the denominator. 1 plus x squared in the denominator. Now, I probably should have put these on 3 slides because what you're going to see is that the arc tangent that you're seeing on this slide and the arc cotangent that are on the next side look a lot like when you compare arc sine and arc cosine. So how different are arc sine and arc cosine? A negative, right? That's all that's different. And in fact, that's all that's different between arc tangent and arc cotangent as well. Arc tangent is the positive, arc cotangent is the exact same expression with the negative on it. And amazingly enough, the same thing happens with secant and cosecant. Just that negative changes. Did everybody get my previous slide written down, or did I move too quickly? You got it? Okay. Okay, I see lots of papers flipping. Anybody still writing? 1? Okay. All right, so I see mostly you guys don't have these stapled yet, which is probably good. So keep that sheet that's got the derivatives with it right next to you so that when we do our derivatives, you can just reference back to it very quickly. All right, so we're going to do some examples, 3 in fact, of finding derivatives of these arc functions. Of course, they aren't just arc sine t, right? Because the whole point is that we want to engage them with the other derivative rules that we know. So this is an arc sine, and we have this new derivative rule that we can use with it. But what other rule is going to have to be combined with this? Well, the chain rule. Is that what you said? Yeah, Jaden's right. The chain rule. Because we have not just t inside, we've got t squared. Now, it's not a very difficult chain rule problem because you know the derivative of t squared, right? That's fine. But you do need to recognize as you're working what's going on. So keeping in mind, I'm going to put the parentheses there to sort of accentuate that. This is going to be a chain rule problem. So I'm going to do f prime of t, and if your t's bother you and you want to turn them into x's, I'm okay with that. Just WebAssign's probably not going to be okay with that, so be careful in there. Arc sine, the derivative of arc sine is 1 over the square root of 1 minus x squared, right? But what is our x? T squared. So you don't necessarily have to write what I'm writing, but what we really have is t squared squared. That's what this really is. And then we need the derivative of the of the inside multiplied by it on the outside next. What's the derivative of t squared? 2t. So this is sort of all the calculus that's involved. The only cleanup you really need to do is to put the 2t on top and to go ahead, if you didn't already, like I had written it, change it to say t to the 4th on bottom. That's it. Okay? That's it. It would be really easy to forget the squaring of the t, though, because it's already squared. So, don't get thrown off by those small details, but do remember that.
So it would be all right to have a radical in the denominator?
Yes, I'm glad you asked that question. So we had encountered that issue earlier where I had a square root 11 in the denominator, and I was like, oh, no, we don't leave that there. The difference between that and this problem is that this has a variable in the denominator, so depending on what this variable's value is, it's sometimes already rational, right? So if we have a variable underneath a radical, there's no need to rationalize it because we don't know whether it's already in rational form or not. We just leave it like it is. That's kind of the default, is if there's a variable there, we leave it. All right, this looks really ugly and messy to begin with. I promise it won't when we clean it up at the end, okay? So we're going to employ several of the rules that you know, the first one being the natural log. So what is the derivative when we have natural log involved? It's 1 over. So it's 1 over, in this case, x, which is the t squared plus 4, right? Excellent. Then we need a chain rule. Abby's right. And the derivative of t squared plus 4 is 2t. Fabulous. So that's half the problem done right there. We clean it up by putting the 2t on top, but it's really done, right? Not much even to clean up on that one. All right, the 1/2 at the beginning is a constant multiplier, so I don't really have to do anything with that. But I do have an arc tangent. So what is the derivative of arc tangent? All right, so 1 over 1 plus x. Well, our x in the problem for arctangent is what? T over 2. So it's t over 2. That looks awful. Let's try that again. T over 2 squared. Okay, so that's the derivative of the arctangent part. But the arctangent has a chain rule inside of it, right? What's the derivative of the t over 2? 1/2. Okay, pretty good so far? Excellent. Okay, so we'd already mentioned the first half of cleaning this up involves simply putting the 2t on top. We have t squared plus 4 on bottom. Over here, I've got a 1/2 in the beginning multiplied by the 1/2 at the end. The order of operations for multiplication doesn't matter, so I can write all that together as 1/4. Agreed? It's commutative property of multiplication. And over here, I have 1 over 1 plus what? How else can I clean up what's inside there? T squared over 4. Okay. Now, operations with multiplication and fractions say I multiply the tops together, multiply the bottoms together, right? Well, the top part doesn't really change. They're both 1s. So let me rewrite this first piece. 2t over t squared plus 4 minus 1. 4 times 1 is 4. So that's fine. What happens when I multiply 4 times t squared over 4? I just get a t squared. And what beautiful thing just happened? Those denominators are actually the same already, aren't they? They are. So I actually have 2t minus 1 over t squared plus 4, or 4 plus t squared.
I feel like these on paper work out so nicely, and then you get to what the sign, and it's like,
Well, you know what? I choose these ones from your book. So it's not like I just picked something on purpose that worked out nicely. It just did on this one. So hopefully some of them on WebAssign will too. Don't know what to tell you. No, they won't. That would be highly unfortunate. Oops. Okay. We've got another one that starts out looking kind of ugly. Maybe, well, definitely it's even uglier than the one before. Let's just deal with it one piece at a time like we've been doing. This one actually has x as our variable in it, so I'm kind of fond of that. I think this one's going to also have quite a lot of writing to do, so I'm going to start with my derivative on the far left. All right, so 8's a constant multiplier. I get to write it down. What's the derivative of arc sine?
1 over square root of 1 minus x squared.
Okay, so 1 over the square root of 1 minus our x, which is x over 4 here, squared. Okay, I need to do one more thing. What is it? The derivative of x over 4, which is 1/4. Okay, everybody good so far? All right. This next piece, I know I have a 2 in a denominator here, but do I really have a quotient rule here? I really don't. I just really have a 1/2. So I'm going to pull the 1/2 out and kind of ignore this piece of it right here. Now I do, unfortunately, still have a chain rule and a product rule. But I just don't want you to think there's really a quotient rule there, because there isn't. All right, so product rule is the overarching rule that we see here. When I do the product rule, I write down the first piece, and then I take the derivative of the second. That's the order in which I do mine. So what's the derivative when you have a square root? Square root of 16 minus x squared. You're probably thinking of it as an exponent to the 1/2, right? So what happens? Okay, so you bring down the 1/2, and then what? You have all the stuff inside to what power? To the negative 1/2. So if you want to deal with it as you go, you can recognize that it's going to be a negative 1/2 power, which the negative 1/2 is going to put it in the denominator, and the 1/2 part of it is going to make it a square root. If you need to see that in a couple of steps, that's totally fine, but eventually you're going to get 16 minus x squared underneath a square root in a denominator. But you still have one more thing to deal with. The chain rule part of it, what is the derivative of the 16 minus x squared? Negative 2x. That's the harder half of the product rule though, right? The easier half is to take the derivative of the x at the beginning, which would be 1. And then to leave the second part, which is the square root of 16 minus x squared alone. And I think I almost have all of my pieces, parentheses, and so forth opened and closed. That truly is all the calculus there is in this problem. There's an awful lot of cleanup in this problem that we can do. In fact, it cleans up just about as nice as the last problem. Before we move to cleaning it up, are there any questions on the calculus part of it, the derivatives we just took?
Where'd you get that last root of 16 minus x squared?
So remember, this is a product rule over here.
Oh, okay.
So I was doing the second half of the product rule, the derivative of the first piece, the original of the second. Any other questions? Okay. So to cleanup we will go. All right, so we have an 8 and a 1/4 here, right? So that's going to give us a 2. I know we could put the 2 on the top of this if we wanted to. I think we're going to hold off on that for just a, well, I'll put it on top. We'll talk about it in a second. Put the 2 on the top. This would be the square root of what? What's going to go on bottom?
1 minus, is it going to be x squared over 16?
It is x squared over 16. We're going to have to clean that up later. We're not going to have a fraction inside of a fraction underneath a radical, and this is not going to happen. But for now, that's what we have. All right, I have a 1/2 next. Obviously, this 1/2 has to be distributed to each of these pieces, like this. Parts of this clean up and parts don't. Like, for example, this 2 down here and this 2 would cancel, right? I have, oh my goodness, I have an x here and an x here, so that's x squared. So I have an x squared in the top. I have that 2 still on the bottom from the outside, the 1/2 that was on the outside. And I have a square root of 16 minus x squared also on the first piece outside. It should be positive. Actually, yes, thank you, because I had a negative here. Let me actually highlight those. I had a negative here and a negative here. Thank you for that. So it should have a positive. The next one should be negative, though, because I have the negative on the outside over here, and I have a positive right here. So the next one will be negative. I have a 2 in the denominator, and I've got the square root of 16 minus x squared in the numerator, 2 in the denominator. Okay, it still looks atrocious, but it's looking better, right? It is looking better. You might look at those last 2 pieces. There's 3 pieces here. The last 2 pieces and say, well, at least they both have the same radical. And they do. That's definitely a plus. The first piece doesn't appear to have the same radical as the last 2 pieces. So the first thing we're going to do is we're going to actually change that fact. We're going to get it so that that first fraction actually has the same radical that's involved. Does anybody have any idea about how we would do that? You're close. Not quite the right, well, you said 1/2. I don't think 1/2 will do it, but we are going to multiply it by something. If I had a multiple of 16 underneath the radical of that first one, that would take care of it, right? But of course you can't just go inserting 16s everywhere. That's not appropriate. So if I put a 16 underneath the radical here to multiply everything by, what would I have to put on top to compensate? The square root of 16, which is 4. Because it's underneath a radical in the denominator and it's not on the numerator. All right, good job, guys. All right, so in the numerator now I have an 8. In the denominator I have the square root of 16 minus x squared. My second denominator now has an x squared, or not second denominator, second fraction. I still have the 2 in front, and I have the square root of 16 minus x squared on the second piece. What was that, the 2 you were talking about? Oh, okay. And we will here in a second, you're right. We are getting closer. You might notice that the second piece right there does not have a radical in the denominator. And in order to actually combine these, all the denominators have to be the same. So we need the radical in the second or the third denominator. What else do we need somewhere that's missing right now? We need a 2, and where does the 2 need to be? In the first one. Okay, so we need 2 in the first one to get the denominator. So I'm going to need a square root of 16 minus x squared in the last one. Okay, I'm going to see if I can copy this onto my next slide. Okay, so I have 16 in the first numerator, plus I have the x squared in the second numerator, minus, what's in my last numerator? Right, 16 minus x squared, and it needs a minus in front of all of it too, right? So like minus parenthesis 16 minus x squared close parenthesis. And then my denominator is the 2 and the square root of 16 minus x squared.
And then you're gonna have to cancel
We are. When we actually distribute the negative in here, what's going to cancel? The 16 is going to cancel. I have a positive 16 at the beginning, I have a negative 16 in the middle. What else do I have in my numerator now?
the 2's on top and bottom.
Right, I have 2x squared on the top. I have a 2 in the denominator with the 16 minus x squared. So Abby's exactly right. These 2's will also end up canceling. And my final result is x squared over the square root of 16 minus x squared. You should feel a sense of accomplishment. Look how beautiful that is compared to where we came from. Like, wow. Just wow. Any questions on simplification through that one? All right.
On our quiz that we're about to